next talk is by Smillie of Cornell University. It's Dynamical Complexity in the Henon family.
But it's not related to this. Okay. Okay. What about now? Well, yeah, that's good. It's just not reverberating. Okay, thank you. Well, I'm very flattered to be a part of this celebration of Jack's 70th birthday. One of my first, my first professional talk was a talk in Warwick, Math Institute at Warwick, and I was giving a talk about affine manifolds, and at some point in the middle of my talk I heard a voice coming down from above saying, perhaps I've made a mistake, perhaps I misunderstand, but have you made a mistake there? It was a very polite way of pointing out that I had indeed made a mistake on the board. And my first thought was I was surprised that the higher beings were taking such an interest in my work and my talk. Then because I didn't see anyone in the audience who had asked the question. Then I looked up, and it turns out that at Warwick there's a kind of back gallery, which is a level above, and it was Jack pointing out politely that I had made some mistake. Well, I feel fortunate that a number of times my interest and his have overlapped, and he's been able to point out mistakes that I've made, and a number of times I've appreciated very much. Very politely, always. Okay, so I'd like to talk about some questions of dynamical complexity in explicit families of diffeomorphisms of R2. This is joint work with Eric Bedford. So the questions of complexity I want to deal with are very much like those that Shishikura discussed in his talk in the one-dimensional setting, but I want to deal with them in two dimensions. I want to look at a certain model family, the Henon family of maps. So given by this formula, so these maps were introduced by Henon as a model system for the study of two-dimensional dynamics. I was talking with Denny Hill last night, and he was mentioning the first time he heard me speak about dynamics, and I was saying I was going to talk about the Henon family, and he said, well, why this particular family? I think he had in mind somehow that we were knocking off map after map, and why had I picked this one to work on? Well, of course, in the field of dynamics, the situation is very different. We have the ability to ask questions that are way harder than we can answer, and it's not really a question of picking this map versus that map. I mean, knocking off different families of maps is more a question of a lot of people are somewhat frustrated with the difficult problems, and let's focus on some maps so at least we'll have something to talk about and we can share our frustration with one another. So, universality is a great thing. And now there are reasons to hope that by understanding individual particular maps, that the ideas that we come up with can be extended to broader classes, and universality is one of these principles that makes this possible. certainly was true in the one variable situation. So there are reasons why you might want to focus on a particular map other than simply comfort of your friends and colleagues. But you won't get that from my result today. I mean, these are abstract reasons. So let me say a little bit about this family of maps, the Henon maps. So why is this a good family? It's kind of a good generic family. They display three key properties that lead to interesting two-dimensional dynamics: expansion, contraction, and folding. So we'll construct a square centered at the origin, and call that square square B, and I've drawn the image under the map. The parameter A can be thought of as the amount that the origin is translated by this map. The parameter B is the amount that the horizontal distance is contracted by the map. Typically, we'll assume that B is less than 1 in absolute value. So in this picture, you can see some expansion, some contraction, and some bending. And it's if we have simply expansion and contraction, then we're in the hyperbolic world, things are pretty well understood. If we introduce some bending, then we're in a more dangerous territory, more interesting territory as well. Okay, so I'll be focusing on the set of points with bounded orbits. If I call that, let me call that set K. So that means that the orbits don't go off to infinity, but in particular, if we choose our domain well, if we choose the right value of R, they are indeed the points that stay in the domain. Okay, so there is in fact, the map's defined on the whole plane, right? This is just a region in the plane, and we're watching how it's mapped. But all the action is taking place here. I mean, if we're going to be focusing on the set of points with bounded orbits, all the action is taking place here. So, oh yeah. Okay, so you can see from the first picture here that when B is not 0, then, well, when B is not 0, then this map is a diffeomorphism, orientation preserving when B is positive, orientation reversing when B is negative. When B is equal to 0, the map essentially reduces to a one-dimensional map. The image of the square, or the image in fact of the entire plane is a line, and to study the dynamics when B is equal to 0 in this rather degenerate case, the dynamics reduce to the dynamics of a one-variable map, G sub A here. And as in Shishikura's talk, we are writing our one-variable maps the way that the real people write them as opposed to the way that the complex people write them. Parameters. Okay, so let me give you here's just a picture, computer-drawn picture for a particular parameter value. So in this picture, these kind of horizontal curves represent the set of points that are bounded in backward time. These vertical ones represent the set of points that are bound with orbits bounded in forward time. And then the intersection of those two is the set of points with bounded orbits. Well, let's see, this is a little bit different. Henon was particularly interested in attractors, and this is not an attractor, because I had to iterate, this is string theory. I had to iterate curves here to produce this map, iterating forward, iterating them backwards. So this is a string theoretic attractor, not a point theoretic attractor, right? So this is Henon would have the appropriate worldview, this is the kind of picture he would have produced. Okay, so, Henon introduced this family as a simple way of modeling some, very simple way of thinking about some actual physical behavior, and we saw that in this morning's talk of Yoko's. Now, in that context, it's reasonable to focus on attractors. It's also reasonable to take your map and perhaps vary it a little bit, but I don't want to do that. I want to focus on this particular map, and my questions about involving complexity are not really related to attractors. So I'm studying this Henon map for slightly different reasons than arose in this morning's talk. So it's very important to me that this exactly is the Henon map. It's not, within 40% or Henon map. Okay, so I want to look at complexity. Since I guess the next talk will tell us what dynamics is, I'm assuming that we don't know yet. So let me just give you an introduction to some of these dynamical concepts. One way of looking at complexity is by, so in one variable situation, we saw already ways of kind of complexity by counting the laps of these maps of the interval, how they were lining back and forth, how that growth, how that rate of lining was growing. Okay, another thing that would have worked equally well in one variable is to consider the number of periodic points, right? So the number of fixed points at the end, and look at that growth rate. That also makes sense in two variables. And in many cases, for example, for hyperbolic maps, this growth rate is this growth rate is a completely appropriate thing to study. In fact, but there's another concept of topological entropy, which is a little bit more robust. In the case of one variable maps, these two concepts are the same. In the case of hyperbolic maps, these two concepts are the same. If you look at, for example, the identity map, however, that has lots and lots of periodic points, but it's not very complicated. So for the identity map, the topological entropy is 0, which is kind of a more appropriate value. So in a way, this is a slightly more robust version of this concept. So we're going to use topological entropy as our measure of complexity and try to understand how that depends on the parameters. Okay, so let me just give you a schematic here of the. So I want to look at some parameter space pictures of this map. Okay, so the parameters are A and B. So these parameters are determining how this square gets mapped through itself. Okay, so let's assume that the Jacobian parameter B is less than or equal to 1. If we take A to be very small, then there is no recurrent behavior at all. So from our point of view, no complexity and no entropy. Entropy is 0. If we take A to be very large, that's a result of Vanny and Matetsky, that we actually get a horseshoe in this family. Maybe compare this with another picture, parameter space picture. All right, so we have two parameters, like the Jacobian parameter and this translation parameter. Right, so our Jacobian parameter is going up and down, and the translation parameter is horizontal. Now this is a picture. No, I don't actually. This is a picture of Al-Hamuli and Mira. They use a variation on the formula, a slightly different formula. So in order to make my picture correspond to their picture, I have to flip it I have to use the fact that it's a transparency and invert it. Okay. Now, what have they done? They are drawing curves where various periodic points bifurcate. Okay, so whenever, for example, this left-hand, to the left of this left-hand curve, there is no wandering set. This is the curve where a period 1 point is created. Okay, that. Right, no non-wandering set. Right. So the demanding intensity horseshoe region, that someplace over here or something, it's pretty far to the right. Harvard Doversforth got a better estimate here for the horseshoe region, which gives us a little green area here. Maybe I should just say what a horseshoe is. This is actually a picture of the horseshoe. Well, it's pretty close to being degenerate. I guess it's not all obvious in the picture that's really expanding. But the horseshoe is a hyperbolic map where the dynamics is topologically conjugate to the full two-shift. Okay, so we code the. That's later in the talk. Right now it's just a picture. Okay, so one particular, the horseshoe is structurally stable. So the horseshoe is something that, since all these curves represent bifurcations, like the horseshoe is over, there are no curves going through this horseshoe region, no changes in that horseshoe region. No bifurcation. No bifurcation there. So I'm going to come back to this complicated picture of parameter space later. So general facts about entropy. So entropy is our measure of complexity here. The entropy varies between 0 and log 2. It's 0 way to the left, log 2 way to the right, from the horseshoe region where the natural full two-shift. The entropy is log 2. Entropy is a continuous function on parameter space. And if we restrict to the axis where b is equal to 0, then the entropy reduces to the entropy of this one-dimensional map. And as we heard before, it's monotone along that axis. Okay, so it's, in general, hard, well, it's, so the one variable picture of entropy is very clear with this monotone behavior. There is not much reason to think that the two-dimensional picture is particularly well organized. I mean, it's really a completely open question whether there is any type of monotonicity going on. There's some reason to think that entropy may not be monotone in the two-variable situation. There are results of Hahn, Jack, and York, which Hahn, Jack, and York would say that the periodic points do not get created in a monotone way. So in that way, it's unlike the one-variable situation, whereas the parameter increases, periodic points are only created; they aren't destroyed. So it's a complicated problem. So one way to approach such a question would be to look at the level sets of the entropy function. Look at the structure of these level sets. So these are, again, it's not easy to get much information about the structure of these sets. But I want to talk about some joint work with Eric Medford where we deal with a very special case. So since this is a hard problem, we're not at all embarrassed to focus on some very small piece of this and some very small piece of parameter space. And let's see, so one of the lessons from the one variable case was that it was really useful to bring some complex techniques to bear. I guess that was kind of the last part of the Milnor-Thurston paper, was introducing these complex techniques to finish the proof of monotonicity. And I think there's a lot of reason to think that the complex techniques would be useful in two variables, but there's also a lot of work involved in getting them to actually get the techniques in sync with the problems. So we're delighted that at least in this one special case, we can bring successfully use some of these complex techniques to get some information about what's going on in the real math. Okay, so here's the problem. Say that F has maximal entropy if the entropy is as large as it can be, log 2. First problem described the dynamics of those maps with maximal entropy. Second problem described the structure of the set of maximal entropy parameters in parameter space. So, here of the one-dimensional situation. I want to make a few additional observations about the one-dimensional situation. So this is a graph of the entropy function as in the one-dimensional case. We can think of, well, this is slightly different coordinate system here. So what we're interested in is not s here, but the log of s. So it goes from 0 to log of 2. And the Milnor-Thurston uses a slightly different parameterization for the map. So entropy increases from the, this is the Feigenbaum, Collet, Cresser point here, up to a equal 2, where it's constant. This is the Ulam von Neumann Chebyshev map here. So let me say a little bit about that. So the Ulam von Neumann map, I tried saying Ulam von Neumann once and was suggested that it had bigger, larger history than that. Is one of these beautiful examples in dynamics where you just get this amazingly elegant structure coming out. So this is the map of the interval where the graph goes completely to the top. In this case, there is a metric on the open interval, -2, 2, for which the expansion factor of the map is precisely 2. Now this metric is it's continuous, but it blows up at the endpoint of the interval, so that it's not. In fact, the expansion at the left-hand endpoint of the interval, which is a fixed point, is 4 rather than 2. So it's Well, yeah. Right. So that's right. There's a nice form for it. I mean, one way of deducing those facts is by looking at a semi-conjugacy with the circle map. But it turns out there's other ways of seeing that those, understanding that behavior in other ways generalize better to three dimensions. Okay, so now I want to return to look at this the two-dimensional setting here. So if we want to understand the maximal entropy locus in two dimensions, well, so I want to start with our first question, which is to understand the dynamical behavior of those maps with maximal entropy. Now, they contain the horseshoes, where we feel we know what's going on, but they also contain non-hyperbolic values as well. And let me say a little bit about what way hyperbolicity breaks down in those examples. So the question is, how does hyperbolicity fail? And in particular, to what extent does the situation in two variables mirror the situation in one variable, where the von Neumann map is the boundary of the maximal entropy locus. I don't think it does. I'm not. Does it have a semi-continuity property in general? No. There's nothing just from the definition. Right? Is that?
Okay. Once you have horseshoe, then you're going to destroy that.
So in two dimensions.
All the entropy is due to the horseshoe, which follows from the horseshoe.
In two dimensions.
Yes, but I see. Okay.
It's a little delicate, right? In two dimensions, there's some structure here. Higher dimensions, that's wrong. I mean, the problem is, of course, that it's defined in terms of multiple limits. There are no easy ways of bounding it from above or below. If it's C infinity, yeah. Right. And that's certainly part of what so in our particular case, we have continuity, and Henon result is part of that. Okay, so the first question is whether periodic points, what happens to periodic points when we go to the boundary of hyperbolicity. Now, just by algebra, by Bezout's theorem, the number of periodic points are less than equal to 2 to the n. On the other hand, Kontakt and Mendoza have a relationship between periodic points and entropy, which gives a one-sided relationship, which says that asymptotically, if the entropy is log 2, then asymptotically the growth of periodic points is log 2. On the other hand, the actual story is much more explicit, which is that if we have maximal entropy, that every single periodic point that can be there is there. So exactly as many periodic points as are in the horseshoe. And as soon as you've lost a single periodic point, you've lost entropy. Okay. If and only if? Yeah. If and only if. So these are actually equivalent. These two conditions are actually equivalent. Okay, so if we want to, this fact is also somewhat useful in nailing down where the maximal entropy locus is. So here's a somewhat simpler diagram who have plotted fewer points than alpha, Mooley, and Mira. This is the period 1 bifurcation line. This is the period 2 bifurcation line. This is where the period 1 point is created, moving to the right. This is where the period 2 point is created. This is where the period 3 point is created. Well, this is the Hubbard-Oversworth horseshoe region. So here, this is a region where we do have maximal entropy. So according to this result, as soon as we cross these lines, we don't have maximal entropy any longer. So the boundary maximal entropy is someplace outside of this and inside of that. This is someplace in this region. But on the real line, we know where the boundary is. It's just exactly that region. Right.
Does there have to be another period 3 or is this zero? Oh, they're both on the same line.
Okay, now recall that over here? No, not in the real line. Not in the real line. But if you were to extend the map to C2, you could see the situation would be different. Right? I'm just talking about real horseshoe here. Right? Okay. So recall that for the Henon von Neumann map, we had some unusual behavior at the periodic points about the exponents here. That's actually mirrored in this two-dimensional situation. If we look at a maximal entropy map here, then we can look at a maximal entropy map. We can look at a periodic point at period n and look at measure the hyperbolicity by looking at the expanding and contracting eigenvalues. So we have, not just that it's a sample point, but we have very explicit estimates on how much it must expand and how much it must contract. Okay, so we recall that in the one variable situation, we have an inequality here. Lambda plus a p would be equal to 2 to the n. In the two variable situation, it's a strict inequality. So it's important that b be not equal to 0. If b is equal to 0, then we have equality here. Well, recall that in addition to having a multiplier of 2 at most points, there was some special point for the one variable case where the multiplier was 4. That's also true in the two variable situation. If f has maximal entropy, it has 2 fixed points, each of which is a saddle. If, for convenience here, we assume that we're in the orientation preserving case, then there's one of those fixed points. So, in the orientation preserving case, one of those fixed points is down there, and one fixed point is up there. Okay. So if we let alpha be the fixed point where both eigenvalues are positive, which is this one down here, then in fact we have a stronger estimate. Lambda plus is bigger than 4, and lambda minus is less than a quarter. Okay. So that, again, situation in two variables mirrors the one variable situation, but with inequalities replacing equalities. Well, again, this gives us information on parameter space, right? This gives us a stronger condition on parameter space. If we graph, here we're graphing not just where the periodic points appear, but where the eigenvalues take on certain values. So when the eigenvalue is 1, that's just when the point is first created. So these are, I'm just looking here at the fixed points. When the eigenvalue is 1, the fixed point is first created. Here's the region where some fixed point has eigenvalue 2. Here's the region where, here's the region where some fixed point has eigenvalue -2. Now, actually, the Ulam-von Neumann map itself has an eigenvalue of -2. So this curve actually goes through the Ulam-von Neumann point, -2. And the Ulam-von Neumann map also has a point with multiplier 4. So this curve also goes through. So we get a finer information here about the boundary of the maximal entropy locus. It must be contained in this region here and that region down there. Let me talk to you afterwards. I need to get. I think the answer is yes, but I need to check definitions here before I. Okay, so what we've shown are a number of conditions that are compatible with hyperbolicity. The property that's not compatible with hyperbolicity is that when we have a maximal entropy map which is not hyperbolic, then we actually have a quadratic tangency between stable and unstable manifolds.
Okay, let's say that the boundary on
well, not a priori, but I'll say more about that later on. I mean, a priori, it could be that you have a tangency that gets created and uncreated, and you haven't left maximal entropy. Right? I'll speak to that in a little bit. So, let's see. So the picture to think about here is a picture like this. Well, so this is actually you're actually in the hyperbolic situation here. You get to the boundary of the hyperbolic situation when this unstable manifold becomes tangent to that stable manifold. And in this case, these are both parts of the stable and unstable manifold at this point over here. That's that point over there. Well, that's the only one that we have a theorem about. Then you lose entropy. Good question. Let me get to that in a bit, okay? Okay. Here's another thing that occurs. Notice in this particular example, when these things become tangent, you get a picture of intersection of stable and unstable manifolds. Looks like that. Picture down at the bottom. Well, that picture down at the bottom is incompatible with expansiveness, right? So expansiveness means that if given any 2 points, they move apart either in forward or backward time. Well, if you take a point there and a point down there, those are on both the same stable and same unstable manifold. So in forward time they move together, and in backward time they move together. Right? So if the map is not a maximal entropy, it's actually not expansive. Okay, because now expansiveness is a topological condition. So we get as a corollary here that if F is topologically conjugate to the full 2-shift, then it's actually hyperbolic. Okay, so topological conjugacy, certainly weaker, hyperbolicity is a priori a smooth conjugacy in variant. Depends on the smooth structure. But according to our theorems, if it's topologically conjugate to the full two-shift, then it has maximal entropy. But it's also, so if it has maximal entropy, either it's hyperbolic or it's not expanding. But the full two-shift is not expansive, but the full two-shift is expansive. So it must actually be hyperbolic. What's the converse? No, there are many hyperbolic examples with smaller entropy. You mean among maximal entropy maps? No, we don't know that. We don't know that. It's a very interesting question. We don't know. Let me give a little more information here. In one variable, what happens when you, so in one variable, when you are to the right of the, when A is greater than 2, then this graph reaches above the top of the square, and the set of points with bounded orbits is a horseshoe, right? When A is equal to 2, the graph just raises the top of the square. The set of points with the bounded orbits is an interval, because it's connected. Okay, so the boundary of maximal entropy in one variable corresponds to a topological change in the set K. The situation is different in two variables. So in particular, I mean, if we want to look at the two-variable version of our map here, then the set K plus set of points with bounded orbits, when A is equal to 2, and that is given by this interval, minus 2, across the real numbers. Now, if F has maximal entropy, and we're in the generally two-dimensional situation, as to say B is not equal to 0, then in fact the set K, the set of points with bounded orbits, is a Cantor set, and this set K plus has no interior. In particular, K is not an attractor in any sense in this situation. So, no, the set K minus does not have interior. Okay, so we've identified if you lose hyperbolicity, then you must have a tendency of stable and unstable manifolds. You must have a tendency of analytic curves. Right, so that raises the question, perhaps the boundary of the maximal entropy locus is itself an analytic set, because it seems to be defined by an analytic condition. Okay, well, the answer is kind of yes. If we look at the intersection of the boundary of maximal entropy with the positive half plane, then that is indeed an analytic set. Or if we look at the intersection with the negative half plane, then that's an analytic set as well. Now, if I can get the right periodic point picture here. So we have some analytic set up here that comes in and meets this point and then leaves at this other angle. Well, that kind of coming at one angle, leaving at another angle is not consistent with being an analytic set. So the union of these two analytic sets is not an analytic set. So the entire boundary is not an analytic set, but in each half plane it is.
It's not connected.
We don't know that each half is connected. No. Yeah, I think the set is semi-analytic. My understanding. I checked with Eric. Semi-analytic. So it's defined not by zeros not just by zeros of analytic functions, but by zeros of analytic functions, inequalities. Pardon? Well, so upper half plane, it's an analytic set. Lower half plane is an analytic set. Stick the two together. It's not an analytic set, but it is a semi-analytic set. Yeah. In fact, it is the intersection of an there is an analytic set in the whole plane of which this is the intersection. Pardon? As far as we know, it can have compact components. Okay. And natural conjecture is it doesn't, right? Natural conjecture is Right. So this doesn't answer the monotonicity question yet. Doesn't answer it yet. I got one more transparency. Which still doesn't answer the monotonicity. Okay, so we can, right, so something's going on in here, and something's going on in there, and then these two sets are meeting here at the origin. So what we can say is that there's a constant B naught, so that for B less than B naught, that is near, when the Jacobian is sufficiently small, the non-hyperbolic maximal entropy locus consists of two regular analytic curves, right? In general, to say a set is analytic does not mean that it's built out of analytic curves, right? It can have singularities, etc. But in this region, when B is sufficiently small, the maximal entropy locus consists of two regular analytic curves meeting at 2, 0, which is the Neumann parameter, and crossing each horizontal once. Okay? Now, often in these situations, where you're analyzing what goes on for a small Jacobian, particularly in the situation of strange attractors, when they say small Jacobian, they mean like way small Jacobian, like really small Jacobian, like 10 to the minus some large power. Our number here is 1/20th, which may seem like a small number, but I want to say that in this context, it's really big. This is a really big number. So at least in this region, and this region extends. Well, so in particular, 1/20th is one of these ticks here on the graph. So you can actually even see it. It's so big. So for this bottom level here, I can't do this with laser pointer, but this bottom level here, this strip here, we can say the picture is just exactly the way you conjecture the picture should be. Okay, so there's nothing funny going on in that strip. In particular, it's completely consistent with monotonicity. Right? You know, can't say very much about monotonicity, except this is not a violation of monotonicity in this picture. Let me give just mention references here. We have two papers which contain contain most of these results. Polynomial diffeomorphism of C2-8 quasi-hyperbolicity and real polynomial diffeomorphism of maximal entropy. These are both available on the Los Alamos preprint, Los Alamos National Lab see, going from 8 here, we've decided to stop the Roman numerals. 8 is the last Roman numeral. And we've gone down to Candace's. Paul Blanchard was suggesting that we follow Sue Grafton's idea here, and A is for attractor, B is for continue the next series of papers. So let me just say briefly what ideas come into these results. The first challenge is to get some geometrical consequence of maximal entropy. That comes out of a joint paper of Bedford, Misha Lubitsch, and myself, where we prove that the complex Henon maps have unique measures of maximal entropy. So when the real Henon map, and we describe very explicitly the support of these measures. So when the real Henon map has maximal entropy, that means that all of the dynamics in the complex Henon map is actually going on inside the real Henon map. The second step is to get some kind of expansion type results, or some kind of metric here which is expanded. So for that we use the parameterization of there's a natural parameterization of unstable manifolds at periodic points. And we use the fact, and on that, on those unstable manifolds, there's a natural green function. So we know that in a maximal entropy situation, the green function is harmonic outside of the real axis. So elementary estimates from harmonic analysis, elementary estimates from potential theory, give us some kind of growth information. Just using the growth of those green functions gives us some information about the growth in terms of dynamics. Then from that we need to that information tells us basically our family of our dynamics is nice in the sense that these parameterizations, if you take limits, they do not get too singular. There's a bound to the singularity of limits of parameterized unstable manifolds, which puts us in the realm of this quasi-hyperbolicity. So quasi-hyperbolicity is like a two-variable analog of the one-variable notion of Mizarevich parameter. So Mizarevich parameter in the sense that critical points are non-recurrent. Then when we know that we're in this kind of generalized Mizarevich context, it gives us a certain amount of combinatorial structure that we can play with and deduce things here in the real case. Then the last result here with this large constant d equals 0.05 comes from a separate approach to quasi-hyperbolicity here, where we use something that's like a very naive version of a Yoko's puzzle in two variables. Part of because it's naive, we don't get, because we build this naively, it falls apart when we get too far away from the one-dimensional situation. But
any questions? There's one over here. Okay, so did I understand correctly that the boundary of hyperbole of entropy over 2 is exactly when this piece of stable manifold intersects that piece of unstable?
that's true in this region. Okay.
And otherwise you don't know that?
Otherwise, we don't. Otherwise, we know a lot. We know that there is a fixed point. Otherwise, we know that there is some fixed point and the boundary consists of the intersect tangencies of that. Well, let's see. It's a question of how you define this. You say this stable manifold intersects this stable manifold. This is not like Clinton's situation. I think the answer is.
The first intersection. I mean the first sentence. Okay, the first sentence.
I think the answer is to say that we've really nailed things down so that you can say this, so that we can say this, when we want to say that this is, yes. But we want to say that this tangency is what's causing the problem. We really have to be in this situation. In general, there could, for example, be components in the maximal entropy locus which don't contain torsions, which we don't know. Outside of this locus, our results are rather abstract. Yes. Outside of this locus, we have no. Yes. Up here, we have no reason to. I mean, when you say could be, in the abstract logical world of mathematics, yes, it could happen, but we have no proof that it doesn't happen. No, no, so tangencies are always quadratic. That's part of our result. But there's no reason why in the boundary there couldn't be creating two tangencies that were occurring at the same time. But our result is, in fact, it's not a semi-analytic set, but it's actually an analytic set. Okay, so it is an analytic set. In terms of tangencies of stable and unstable manifolds. It is defined in terms of tangencies of stable and unstable manifolds. Right. Takes work. I mean, it's not. Yeah. Right. No, that it is not. It's not. The step from first statement to second statement is not obvious. We have to nail it somehow. Show that there are countably many potential tangencies. You have to show that only one of these, or only a finite number, are relevant to defining that potential. Well, no, if we have two analytic, there's not a corner. We don't have a corner. No, so we don't have. Oh, black and white and white. Right. You could have. Right. That could have. Right. Two things that cross each other divide the plane into, 4 quadrants. Right. So you could have a situation where the boundary was in the set was in the first quadrant and the third quadrant. As far as we know. Well, with some more thought, perhaps. I'm not saying. Well, I'm distinguishing here between the pictures and the theorems. But I don't know. I don't know. I mean, we have to. You may be right, but I'd have to listen for a while to understand. You're saying with some thought here, maybe I could say more. That's why I give these talks. That's why I give these talks, so people can point out to me where further improvements can be made. One of these, this happened once with Andre. Some of these, the result that K, the result that K is a Cantor set here in the two-variable situation was inspired by exactly such a remark by Andre, saying, you must know more than you pretend to know here. So I was happy to have further conversations about Well, oh, you mean in this case? Yeah, we can follow it. It is, again, a tangency. It's just that the tangency, the relevant tangency in the orientation preserving case is different from the relevant tangency in the orientation reversing case. So both of these curves extend to curves of tangencies. It's just they become no longer relevant. So